Okay, so let me start. Um, what I will do is I will introduce the company. I'll just take 2 minutes or so and introduce the company and myself, and then we will go right in the presentation. I'll talk for like about 2 or 3 minutes, or maybe like 5 minutes on specific topics, and then I actually recorded a video and I will play the video for 15 minutes. And this video will cover a whole bunch of topics. And once that is done, then we can do question and answer session. I believe we set it up for an hour, but it's only going to be a half an hour webinar. So let me just introduce the company. So my name is Ada Sayed. I am the field application engineer at PFC Flexible Circuits. PFC Flexible Circuit is a specialized shop which specializes in making flex and rigid flex boards. We are located in Toronto, Canada. We were acquired by OSI in 2018. We have a sister company in California as well called AltaFlex. PFC has been around since 1997. We currently have about 180 employees, and we do full manufacturing and assembly in-house of flex and rigid flex circuits. Now, when it comes to the technology, we can do, we can do as tight as 2 mil line width and tolerance, which is a little bit design dependent, but 3 mil line width and spacing is our standard, our sweet spot. We can do everything from micro via, buried vias, stacked vias in rigid areas of the rigid flex, and we can do HDI stuff as well to a certain degree. That being said, let me start by covering the topics. So the first three topics, technology, material, and lead time, is what I want to talk about. And then the rest of the topics below are part of the video. So technology, when it comes to line width and spacing, I'm sure you have heard this a lot, that once you lower the line width and spacing, the price of your flex will go up. At some point in time, that may have been true, but at this point in time, in 2024, as far as I know, most of the companies use LDI technology, right? So with LDI technology and with advanced plating features, some manufacturers use MSAP, ASAP, whatever, different technologies for plating and etching and all those things. 3 mil line width and spacing is quite standard, and a lot of companies can actually do lower than 3 mil, so they can go down to 2.5, 2.5, even 2 and 2. So I don't think that at this point in time it's true, so much true that if you're designing your flex circuit with tighter line widths and tolerances, tighter line widths and spacing, then your pricing will go up. What happens is, when companies advertise as standard and then advanced and ultra advanced features that they can handle, um, when it comes to ultra advanced, let's say 2 mil in line width and spacing or lower, those properties or those variables may be okay. They may be design dependent. What that means is, we would have to review your design and say whether we can make it or not. So you're really pushing the limits, right? So what I'm trying to say is, not every company can do the most advanced features on every design, not in a mass production. Now, I will say that 2 and 2 is something we do at PFC, we do in production, but on specific design. So it's very design dependent. 3 and 3, not a problem. So that's what we mean when we say is, when you lower your line width and spacing, your price will go up. It's not necessarily for everything, but a lot of time when you're really pushing the limits, because then we will be producing the boards on a smaller panel size, right? For example, for PFC, we have 12 by 18 and 18 by 24 panel size. 18 by 24 panel size is more cost effective, but when we are doing really tight line width and tolerance, we will be using a smaller panel size of 12 by 18. That means your labor cost remains the same, but now you're producing less boards per panel because you're using a smaller panel size, so your pricing will go up. So yes, it does affect, but it's not always the case. It is very limited these days. Material, another topic, very interesting topic, because I hear this a lot, that, oh, well, certain materials are more expensive. And well, the thing is, when you're choosing a material as a designer, when you choose a material, you don't choose based on price. You choose based on the requirements of your application. So there's no question about, there's no reason to talk about pricing at the design state. Where is the pricing coming from? Where is the price difference? Well, here's what I think. This is how I see it. Sometimes when customer come to us and say, please produce this in 3 weeks, this board in 3 weeks. Now they may be asked, let's say they're asking for 3 panels, and it's a 4-layer board, right? So 3 panels, meaning I'll be using 6 plies of laminate. So 3 panels, 6 plies of laminate. Now, if this material is something which is out of ordinary, maybe some funky material, I would have to go to my local supplier and ask them to provide that material. Now, those material may come in specific MOQ. So let's say they may say 10 pieces or 15 pieces. So if you're asking for 3 weeks, I probably want to get the material as soon as possible. And if I'm trying to expedite the material, I would end up paying the expediting fees and the MOQ price. So that's something you can consider as a designer or on the design side. Let's say you're a commodity manager or purchasing manager, sales manager, whoever. You can consider this, keep this in your mind when you're ordering your FPCs. You can ask your supplier, hey, what's the MOQ on material? Do you actually have MOQ or you're okay? Because if there's an MOQ, maybe your supplier is charging you for that price, right? Or if you're asking for expedited delivery, let's say 3 weeks or less, they may be charging you for expediting the material. So you can decide, you can ask your supplier, are you paying this expediting fee? If they are paying, then you can decide, without the expediting, is it okay if your board is delayed by another 3 days? Because a lot of time you can get the delivery in 3 to 5 days. With expediting, you can get it in 24 hours. So you can decide if you want to pay that extra amount of money to expedite the material or not, and the MOQ. So maybe your supplier will say, well, the MOQ is 10 panels. Well, if it's 10 panels, then your 4-layer board goes from 3 panel to 5 panel. Maybe you want to buy a little bit more boards, and that way you can have a little bit more boards and actually lower the price. So that's what I think about material. Lead time. Now, lead time, Flex is a premium product. So lead time is something every company is different. Like, for example, for us at PFC, we are a predominantly production shop. Our sister company in California, they are a very quick turn shop. So quick turn, when you ask for a quick turn, quick prototype, there will always be extra costs. 24-hour turn, companies will charge you 200, 300% maybe. So you have to decide on lead time whether you want to pay extra money or not. And for lead time is different for every single company. So you would have to figure out which supplier is best for you, and if they can provide the lead time without charging you shorter lead time without charging you extra money. So that's something you need to negotiate with your supplier. Okay. That being said, the next couple of processes, what I want to do is I want to play a video, and this is a 15 minutes video that I recorded. And after the video is done, we can do Q&A session. All right, so let me play the video.
A lot of times, designers ask for laser routing. When I ask them why, they always say because it's better. Question is laser really better?
Request. And that is to have sharks with frickin' laser beams attached to their heads.
Laser routing is great. Laser is very accurate, like plus minus 2 mil for overall dimension, and makes beautiful edges. However, it is very expensive to operate. It can only make one panel at a time. Since the laser is energy, it also adds a lot of cost to operate the laser machine. Other problem is that laser leaves carbon residue. Important thing to note here is that it can only route 1 mil deep at a time. That means if the flex is 8 mil thick, it would cut the same location 8 times to get through the flex. In the end, there will be carbon contamination. Then the quality department would have to use alcohol wipe to clean the boards and remove contamination. We can never remove 100% carbon. All of this adds a lot of cost and adds to lead time. There are more cost-effective alternatives to laser routing. There seems to be a misconception that flex circuits cannot be routed on mechanical routing machines. Mechanical routing is great because the machines usually do 5 to 6 panels at a time. We can even stack panels to double or triple output in some cases. Mechanical routing can hold plus minus 5 mil tolerance. The edges are not as good as laser, but it doesn't mean that they are bad. Okay, depending on application, mechanical routing may be sufficient. The reality is that in most cases, you probably don't need to hold plus minus 2 mil tolerance. So plus minus 5 mil tolerance on overall dimension is standard. As a matter of fact, most designs come with plus minus 10 mil tolerance. If you're not convinced, you can always ask your FPC supplier to cut few pieces of FPC material and send it to you for testing. There's a special type of mechanical drilling routing machine called Vision Drill and Route Machine. The beauty of this machine is that due to built-in alignment features, it can also hold a tight tolerance similar to laser machine like plus minus 2 mil. Not only that, it can even hold plus minus 0 mil tolerance if needed. Of course, these scenarios will require some special toolings, but can be done. Since such tight tolerances are not common, these machines are usually used for special jobs only and not for regular production. Therefore, instead of using 5 or more spindles, they usually come in 1 or 2 spindles. Spindles, you could say, are the vertical drilling arms that you see in the video. Although cheaper to operate than laser, but due to single spindle, the production is not as efficient as regular mechanical routing. Die punch is a great alternative to laser routing. All circuit boards, whether it's PCB or flex circuits, are manufactured in panel form. Manufacturers price your boards per panel, not per board. MOQ is usually based on panel. Once the production quantity goes over 10 panels, die punch is cheaper than all other routing options, including laser, mechanical, and vision routing. There is, however, an upfront cost for die punch. Now, die punch comes in 3 different tolerances. Option 1 is wood die, which is plus minus 10 mil tolerance, cost between $400 to $600. Option 2 is a metal die, comes with plus minus 5 mil tolerance and cost between $1,200 to $1,600. And option 3 is male-female die, which is pure metal, and it can hold plus minus 2 mil tolerance and cost about $6,000. Remember, only option 3 is truly expensive one, and it is direct competitor to laser routing. Even though it sounds very expensive, but after 20 panels or so, die punch will be cheaper than laser routing. So in conclusion, what I would say is that although upfront cost of die punch is scary and scares away most buyers, it is actually the most cost efficient option for anything which is over 20 panels. I wish all circuit boards were this shape. However, flex circuits are never standard size with few exceptions. As I mentioned before, manufacturers' price is based on panel, not boards. Your board price depends on how many pieces we can put in our manufacturing panel. We basically take the price of a panel and divide it by number of boards per panel. The shape and size of the board determines the material utilization in the manufacturing panel. Now, I understand that the size and shape of your flex circuit is determined by your product needs, but I just want to take a moment to share with you how the pricing works at the manufacturer. As you can see, the amount of wastage per panel, just remember you're paying for it. And at this stage, it's not just the material cost, but the panel is at the last stage of manufacturing. That means the cost of processes and the labor is built in it. Since flex circuits are flexible, we need to use stiffeners under the component areas to ensure solder joints don't get broken. The stiffeners can be FR4 material, stainless steel, aluminum, copper, or even polyimide material. Placing stiffeners is a time and labor intensive and costly process. Each stiffener is placed manually one at a time. The process is basically a three-step process. Number one, place the stiffeners. Number two, place boards in a panel for lamination. And step number three is lamination process. The three processes combined can take many hours. If place stiffeners on both sides of the flex, it will actually increase the price. If you use different thicknesses for stiffeners, that will also increase the price even further. So the plate that you see operator putting on top of the stiffeners, that has to be routed. So if you have stiffeners on both sides, we would need two different plates. So one for bottom, one for top. But also if you have different thicknesses, then the plate has to be routed with different cavities or different thicknesses. So it adds a lot of fixturing or tooling cost as well. Designers need to take these considerations into account when placing components, because your stiffeners will be placed based on your component locations. So if you're placing components on both sides, then you would need to have stiffeners on both sides. Now I'm talking about pure flex, not rigid flex. Rigid flex is a different story. So if you're a buyer for your company, try explaining this to your designers. And if they still don't get it, of course, cover coat is the way to go on the flex. But the problem with cover coat is that it is a film, a piece of material, and it has to be routed. It is so thin, and that is why it's always routed on a laser machine. And due to routing, it cannot be routed for fine pitch components. This is why we have to use solder mask in areas with components with fine pitch, and we end up using cover coat plus solder mask combination. It does add cost because application of cover coat and application of solder mask are two different processes. Cover coat has to be routed and then pressed during lamination, while solder mask is a chemical, and therefore it has to be applied and then baked. Both are time-consuming processes. Now, when you combine both processes, price will definitely increase. When it comes to assembly, flex circuits are not same as PCB. PCBs are rigid, so you make an array and voila, you go. But when it comes to flex circuits, we have to have some kind of fixture, some kind of pallet, and we have to put the flex on top of a pallet in order to stabilize the surface, in order to make it flat. Now these pallets can add a lot of cost. We call it fixturing cost. So let's say you have a flex and I need to create a pallet for it. The problem is most of the assembly or contract manufacturers, they wouldn't make the pallet themselves. They will design it and they will probably send it outside and have some third party make it for them. These pallets are usually made out of material called Durastone, and each pallet could cost anywhere between $800 to $1,500. Let's say I'm doing the assembly for you, so I would have to design the pallet and then have it made. If I made a mistake, that money is gone down the drain, right? So what happens is a lot of companies which are flex manufacturers, they also do assembly, because flex assembly is very complex. It could get very complex, and that's why flex manufacturers usually have assembly capabilities as a value add. Sometimes what we do is we make fixtures using FR4 boards, meaning instead of using Durastone, we will actually make the fixture using FR4. We will just take a piece of FR4, etch it off on both sides, route it, make the cavities, route it to the dimensions we need, and put them together. So this way we can save a little bit of money, like flex manufacturers compared to contract manufacturers can save a little bit of money in fixturing costs because they have the manufacturing capability in house. However, regardless of that, all I'm saying is fixturing cost is a lot of cost. And if we are running a larger quantity, then we wouldn't just make one pallet, we will make multiple of these pallets. Now, as a designer, how can you reduce this cost? Well, you cannot. I'm simply sharing so that you can understand where the cost is coming from. Maybe you can reduce the assembly cost if you have, let's say, a smaller flex circuit. You can actually nest it, right? You can rotate 180 degrees so that you can fit them better, and you have multiple of those in an array. That way you can actually reduce the cost of your assembly, nested panels. When we manufacture flex circuits, we always test, we do 100% testing. So we use a bare flex panel, put it on a testing machine, run a testing program, and the machine will test the panel. However, sometimes customer asks us to assemble the flex as well. So when we assemble, depending on the complexity, sometimes customer asks us to test for them. So we call that functional test, meaning now we are testing for the functionality of the flex after assembly. Now it adds extra cost because it is additional cost, and the reason is we would have to build fixtures to make so that we can test the assembled boards. And as you can see in the video, I have a lot of fixtures, and these fixtures were built by us at the factory, and we have to build these fixtures so that we can test your flex circuits. Now these fixtures are these fixtures are PCB on their own. So we would have to design this PCB and make this PCB so that we can test. Now the question is it necessary for you to ask your flex circuit supplier to actually test it for you? Is it possible, here's the question, is it possible that on your end as a designer or as a hardware engineer, can you test it on your end? Meaning, what if you have a machine or a process where you're assembling everything, and when you turn on your machine you would know if your flex is working or not? If that's the case, then maybe you want to avoid having your supplier test it for you because you're paying additional cost anyways. Packaging is such a simple concept and such a simple process. However, this process can add a lot of cost to your flex circuit. And one way it actually adds cost is very common. I've seen this is very common where customer asks us to pack their boards individually. Now I understand you probably we want them packed individually because you're thinking maybe if you put them together they will get damaged. And yes, I agree, they can get damaged if they are together. But you have to understand that you have to keep this in mind, that when you ask for individual packaging, it's time consuming, and it's time consuming. It's less to do with the amount of material we're using and more to do with the time consumption. Imagine every single piece that you're asking needs a serialization. So if we need to do serialization, an operator will have to put a sticker on every single board. They have to individually wrap it, put them in ESD bags, and it just goes on and on. So if you really need it, fine, you need it. But I'm just saying that it adds a lot of cost. So one way of doing a more effective way is that we use some kind of trays, because in this manner we can actually put a whole bunch of boards in the same packaging, but yet they are still separate from each other. This is one way of saving costs at packaging. Now if you do get a tray, then that adds a little bit of inventory on your side. You can either garbage it or send it back to your supplier. It all depends on what kind of trays are being used. If they use special ESD plastic trays, then you may want to send it back. If they are just foam, they can be discarded, but having your board shipped in a tray is much better than having them wrapped individually because that's adding extra cost.
I want to bring your attention to this right here. I talked about Soromas plus cover coat combination. So as you can see here, in these circuits, we are actually opening up the whole area in cover coat and doing Soromas, because the minimum that we can cut cover lay is 6 mil. And in most cases, these right here, the Soromas dam would probably be like 2 to 3 mils, right? So that's why because cover coat cannot be cut so tight. So in this case right here, you can see all this area is just opened by Soromas, and then it's cover coat. So two different processes. They do add cost when you do it together. So it's up to you. Well, I mean, there's nothing you can do as a designer. If there's a component you're using which has tight pitch, you're stuck with it, right? So that's just the way it is. Quick point on stiffeners, different stiffeners, FR4 polyimide aluminum. It's not steel, it's a stainless steel and copper. The application is pretty much similar for all of them, but they do have a different pricing. Like for FR4 and polyimide wouldn't be much different because we would carry those material in-house anyways. But when it comes to FR4, we would have to take a regular, let's say 370 HR material and etch it off. Okay, we will etch it off. So that's actually adding cost. So etching it off and then drilling it and then putting it, so you can see the process steps. There are a lot of process steps involved just to make a simple stiffener. So everything has a labor and processes involved behind it. Stainless steel would something be where we just buy it, or aluminum. Stainless steel and aluminum would something be that we just buy it and we just route it and using a PSA or some kind of adhesive and stick it to the flex, right? So if you notice in the video, during the laser routing, the operator actually used his hand to clean the cover coat when he was putting on laser routing. Now, in case you're wondering if it's a good practice or not, well, at that point in time, at that stage, it's just cutting the material. So we are cutting cover coat on the laser machine, and at the same time, we may be using mechanical machines to cut the laminate. Okay, so in the end, we'll be putting it together. So there are many steps after this step where we will end up cleaning the material itself, cleaning the cover coat. So I know it doesn't sound right touching the cover coat with your hand and cleaning it, but really at this point in time, it's all dirty. Everything's dirty, and it will go through a cleaning process later. So that's why it's okay to touch the cover coat it's okay to touch the cover coat with the bare hands. Second is, why is the operator using standard irons at the stiffener process? The stiffener process, what we do is we need to activate the adhesive when we are attaching the stiffener. So those irons, they are set on very low heat. They're set on just hot enough to activate the adhesive, and that's it. So it activates the adhesive, you put the stiffener with it against your flex circuits, and if you notice, the lady actually put the iron on top of a whole bunch of flex, and that's just to keep them warm. That's it, and it's done on purpose. Then if you remember the video, there was a gentleman who was putting those boards in a pallet, okay, in a panel. So once he's done doing that, they will go in the real pressing. Okay, they will be pressed at a very high heat, very high pressure for like 4 hours or so. So at this stage, what you saw in the video is just to activate the adhesive. It's not really thermally bonded at this stage. And the third is, are the fixtures for an assembly kept clean? And you could see that I was touching a whole bunch of fixtures, a whole bunch of pallets, and there were a lot of pallets. They are kept in a clean environment, but sometimes we have customers who don't order anything for 2 years. So they don't auto for 2 years, those pallets are just sitting there stacked against each other, and they may acquire some dust. But that's why we have clean material handling procedures in-house. And what operators will do is every time they take those pallets, they will actually clean it, and they will be cleaned before they're used for production. For tighter pitch connectors, does it tend to be more economical to use solder mass and have good yield, or just to use cover layer, clear the area with no solder mass dams and just deal with the poor yield? Well, if we are talking about flex circuits, break out the flex from any, okay. If you're talking about the flex circuit, then your flex circuit needs to be under a cover coat, right? If you don't have cover coat, then your copper layers are exposed. You don't want that. So you would have a cover coat anyways. So if you have a flex circuit, you're gonna have a cover coat, and the areas where you have those fine pitch connectors, you need to open it with solder mass. If you're not open and have solder mass around it, so you're opening the cover coat and you're just putting the solder mass. Now, if you don't put the solder mass, well, you can have. There are times when what we do is where we just open the cover coat and we don't have solder mass at all. We just open the cover coat and make sure that the copper feature is covered by some sort of finish, like usually Enig. So yeah, we do that a lot where we don't have solder mass opening. We just have a cover coat opening, Enig, and the connector goes in and we just solder it over there. So that's what we do. So you don't always have to have solder mass. You can actually get away without using a solder mass. Okay, is the solder mass a big cost adder? Well, it adds some sort of cost. I don't know the cost breakdown because it's a process. So if you have a simple board, let's say just a 2-layer board, standard flex, and you do a solder mass on it, because the board is already simple enough, the solder mass cost adder will be larger. But if you're doing a very complex board, which has many stages, and then you do a solder mass, the solder mass adder will be less because your board is already expensive enough. So is it a big adder? I don't think so. In most cases, no. Is the cover coat opening accuracy the same as solder mass? No, it's not. That's, well, okay, accuracy is actually better. Cover coat, almost similar, but cover coat cannot go in a tighter space, so it has to be open larger. Actually, let me rephrase what I said. Solder mass has better accuracy because solder mass is done using film. So you will create a film and then you will put it on with the small features. You put it on your circuit and then you apply the chemical. So you can get better tolerances with solder mass. With the cover coat usually requires 6 mil registration back and forth. So solder mass is better. But again, when it comes to tight feature, you always use solder mass. You cannot use cover coat anyways. So I hope that answers the question. Okay, so let me go back to Robert Moss' question. Can you break out the flex from any layer on the PCB? Technically, yes, you can. It will be an unbalanced stack up. It can be done. We always advise to keep the flex right in the middle. So if you have a 6-layer PCB, we would advise, let's say you do layer 1 and 2 as a rigid, and then your layer 3 and 4 is a flex. So let's say this is your rigid flex and the flex is sticking out. So you can have layer 1 and 2 rigid, 370 HR or whatever. Then you have flex layer here and it's coming out, which is layer 3 and 4. And then you can have a rigid layer 5 and 6. Now you got to keep in mind that flex, when you're using flex, the flex material can be a layer at the whole, in your whole circuitry of the rigid part of your rigid flex. You can have the flex material as a layer. So you can do a balanced build, or you can also do an unbalanced build. Unbalanced build have sometimes little bit of issues when we are handling it during process, but it's not a killer. Can be done. Okay, let's see if there are more questions. Is there a significant cost difference between mechanical or laser drill vias? Yes, there is. But here's the thing with mechanical drill, the minimum we go is 6 mil holes. Okay. And laser we use for 4 mils and below. So if you're doing a micro via, you have no choice but to go laser. So anytime you do a micro via or blind via, sorry, not micro via, blind via, we have to use, if we do a blind via, we have to use laser because blind via most cases is going to be really small, 4 mil or smaller. So it's even though there's a price difference, but it all depends on what you're trying to do. So the price difference, anytime you have blind via or micro via, you will see the cost added. But the cost is added, as I said, it has nothing to do with can we switch between the machines? We cannot. So those processes are fixed. So the cost will be there. Now, if you were saying, if you're looking at, let's say, a double-sided board and you're drilling a small via, let's say 4 mil via, can we drill with 4 mil through hole via? Can we, if we were to do it with laser versus mechanical, I would say there will be a more cost drilling laser than mechanical, because in mechanical, as you saw, I can drill 5 panels at a time. In laser, you can only do one panel at a time. So the labor cost adds up. And I believe the operating the laser is definitely more expensive than mechanical. Is there a difference between cover coat and cover lay? No, it's exactly the same thing. I know I switch when I'm talking. I switch between cover coat and cover lay. It's exactly the same thing. There's no difference. Does FPC do impedance control? PFC do impedance control? Yes, we do. Impedance control, we usually, our standard is plus minus 5%. We can also do plus minus 2.5%, but that's really pushing the limits. 5% is standard. If you had to solder a surface mount connector with through hole mechanical pins, what would you suggest? Like HDMI on USB-C connector, the mechanical pins are through hole, but signal pins are surface mount. Yes, we do that all the time. Okay, yes, we can do stiffeners with plated through hole. So now what happens is, if you want plated through hole stiffener, basically that's a double-sided board. So what we do is we take the board, we go through the whole double-sided board process, and we just etch off all the copper, but the holes will have plating around it. So that's pretty much a double-sided board. Even though it doesn't look like it, it's a double-sided board. And yes, we can do it. And HDMI or USB-C connectors, now I understand what you're saying. And yes, we do it. All the through holes at PFC, we do it by hand, although we do have a selective soldering machine which can do connectors automatically, so through holes. But we do USB-C and HDMI connectors all the time. So what we do is we will do it by, let's say, sometimes we do it by hand and the through holes, and we will do the SMT by hands as well in that case, because it's not efficient to do half the connector on SMT and half by hand. So we would actually end up doing the whole thing by hand, the SMT parts and the through hole parts. So at PFC, we do have a big department for hand assembly. For mass production of a design that requires 2 rigid boards, will be connected together, which would you, rigid flex, hot bar flex with connector, other options? Now that's a very interesting question. If you do a full rigid flex, meaning you have a rigid flex sticking out and on the other side rigid, so it's a rigid flex or rigid flex and then rigid flex, that is the most expensive option. Okay, it will be expensive, there's no doubt. Other thing is you can have a rigid and flex is sticking out on the other side. You just have you can have a connector or solder it directly on your PCB, like hand solder or something. You can do that. But really, it all depends on your design. I really cannot answer without looking at the design, because a little variable change in the design can change the whole thing. There are many times when we have sat down with designers and they had something else in mind, and in the end we ended up doing totally different. So I really can't answer without looking at the design. But all I can say is rigid flex is the most most expensive. If you can do you can also do a rigid, and you can use a flex as an interconnect. So you have a flex, just a flex board with SMTs on both sides, and you just solder them on flex on both sides. You can do that if it's possible. All right. Do you support hot bar soldering on soldering flex PCB to rigid? We don't. Yes, we do. We have done hot bar soldering, and we continue to do that once in a while. And there's nothing wrong with it. If it's needed, it can. I know in Asia they do that a lot, but here in North America, not so much. There are a few places who do hot bar soldering. Again, it depends on small quantity or large quantity, but hot bar soldering can be done. So this was set up in a Teams meeting. So you have my email. If anybody has any additional questions, please feel free to send me an email and I can answer you. So with that, I don't know if anybody has more questions or not. I'll wait a minute. If not, then we can conclude. All right, everyone, thank you very much. I hope it was good for you. And if not, please feel free to ask anything you want. Thank you very much and have a nice day.